In today's lesson, we will continue our discussion of simple harmonic motion and see how some of the concepts we developed can be used to solve problems. Well, let's start by discussing the concept of energy of a simple harmonic motion. Let me ask you this. If you stretch a spring by a vertical distance of y, how much is the work done for stretching it? Anybody recall that? Work done in stretching a spring by a distance y. Well, I'm sure some of you recall from our Physics 1 lessons. When a spring is compressed or stretched by a distance y, the work done is stored as potential energy. So when a spring is stretched by a distance y, the work is done to do that, and that gives the spring potential energy. And the amount of work done is W equal to 1/2 k y squared, where k is the spring constant and y is the displacement. I hope you recall that now. Well, now the total energy when the oscillation continues, what we discussed in the last class was that the potential energy changes back to kinetic energy, and the kinetic energy changes to potential energy, and so on. That means at any given instant, the energy of oscillation has a potential energy and a certain amount of kinetic energy. Is that right? Now, when the displacement is y, the potential energy is 1/2 k y squared, and if at that time the velocity of the object is v, its kinetic energy will be 1/2 m v squared. How about the extreme position? Tell me, what is the velocity of the oscillating object at the upper extreme? At the upper extreme, the displacement y has a maximum value, which is a, is that right? And what will be the potential energy at that time? So at y equal to a, there is no kinetic energy because the object comes to a stop there. All the energy at the upper extreme is potential energy. At the upper extreme, the kinetic energy is 0. The potential energy is 1/2 k a squared. And therefore, what is the total energy at the upper extreme? The total energy will be only made up of the potential energy. But all we need to do is replace this y by a. So the total energy will be 1/2 k a squared plus, what will be that quantity? When v equal to 0, the kinetic energy is 0. So the total energy is 1/2 k a squared plus 0, or it is equal to 1/2 k a squared. Now, although the potential energy and the kinetic energy keep changing, the total energy will not change. So, if the total energy at the upper extreme is 1/2 k a squared, what will be the total energy at the equilibrium? It should be also 1/2 k a squared. What will be the total energy anywhere when the object is oscillating? When the object is here, its total energy will also be 1/2 k a squared. Why? Because the conservation of energy tells us that energy can be changed from one form to another, but the total energy has to be a constant. The potential energy and the kinetic energy can change, but the total energy will not change. That means the total energy of a simple harmonic oscillation is 1/2 k a squared. And this is particularly important for oscillations of a loaded spring, where k is the spring constant and a is the amplitude of the oscillation. Well, when does the oscillating object has a maximum velocity? Tell me, when do we have maximum velocity? Well, maximum velocity occurs as the object reaches the equilibrium position. Is that right? Yes. That means at the equilibrium position, the energy is purely kinetic. There is no potential energy at the equilibrium position. At the equilibrium position, K equal to 1/2 mv max squared. Velocity will be a maximum at that position, and the potential energy will be 0. All right, let's now look at the energy variations of an oscillating spring. This time, I have the spring oscillating in a horizontal plane. That means instead of using y for displacement, we will use x. Is that right? So the total energy, the potential energy this time will be 1/2 kx squared. And the kinetic energy, of course, will be 1/2 mv squared. All right? So an object of mass m attached to a horizontal spring is pulled to the right and released. Now this is the equilibrium position. This is the right extreme. When it is released, it will move to the equilibrium position. And will go to the left extreme and will oscillate between the left and right extreme. Let's see how the total energy varies. Can you talk about it? Well, the potential energy and the kinetic energy will change. At the equilibrium, all the energy is kinetic. And as you move to the left extreme, that kinetic energy gradually gets less and less, potential energy increases. At the left extreme, all the energy is potential. There is no kinetic energy. Well, look at this diagram. Here I have a diagram of how the energy, the potential energy and the kinetic energy change with time. Well, that is x, the displacement. You can see this is x equal to 0. The maximum displacement is a, and the minimum displacement is negative a. That means the object oscillates between positive a and negative a. Is that right? Tell me, when x is maximum, potential energy is maximum, kinetic energy is 0. Look at the 0 values of the energy. Now, when x equal to 0, x equal to 0 means the object is at the equilibrium position. The potential energy is 0, kinetic energy is maximum. When x equal to negative a at the left extreme, all the energy is potential, kinetic energy is 0. You can see how potential energy changes with time, how the kinetic energy changes with time. How does the total energy change with time? Anybody tell me? How does the total energy change with time? Well, the total energy does not change with time. It will remain a constant. You see that? Total energy is a constant. It does not change. There you are. And x, you can see here how x is a function of t. X equal to a cos omega t. Why? Because we said at t equal to 0, x is at the maximum value. So this is a cosine function, and you can see how the cosine function graph looks. Okay, let's now talk about the maximum velocity of a simple harmonic motion. Tell me, where will the object have the maximum velocity? Maximum velocity occurs at the equilibrium position. Is that right? And if V max is the velocity at the equilibrium position, the kinetic energy there will be 1/2 mv max squared. What will be the potential energy at that time? Potential energy will be 0. So what will be the total energy at the equilibrium position? The total energy will be 1/2 mv max squared. But we defined another way of obtaining the total energy. What is that? 1/2 Ka squared. So 1/2 mv max squared equal to 1/2 k a squared, can you solve for V max from there? Well, it's easy, is that right? You can see 1/2 and 1/2 goes from either side. You have divided both sides by m, and what does it give you? You got V max squared equal to k over m a squared. Is that right? That's very simple. And therefore, what is V max equal to? Take the square root of both sides. So, solving that gives me V max equal to square root of k over m times a, where k is the spring constant and m is the mass. The maximum velocity is square root of k over m times a. Let me see if anybody remembers. What is square root k over m? In the last lesson we talked about it. What is square root k over m? Can you relate it to some other quantity that we learned before? Well, that's omega, if you remember. Omega is square root k over m, so maximum velocity is omega a. What's omega? The angular frequency, which is, can you write that in terms of the period? 2 pi divided by the period. Okay, let's move on. So at the equilibrium, all the energy is kinetic, and the maximum velocity there will be a omega, omega a. Let's now talk about some important formulae for problem solving in oscillation so that we can use them to solve problems. The displacement of a simple harmonic motion. Anybody tell me what is the equation for the displacement of a simple harmonic motion? Well, displacement is y equal to a sine omega t plus delta. Now remember, whether it is a sine function or a cosine function depends on when we start our clock. If it's a sine function, it means when t equal to 0, this delta equal to 0. Is that right? At the equilibrium position. Okay, so that is the position function or the displacement function. What is the equation for the velocity of a simple harmonic motion? Velocity is a omega cos omega t plus delta. We talked about that. What about the acceleration? The acceleration is negative a omega squared sine omega t plus delta. And if you remember, we can now replace a sine omega t plus delta. What is a sine omega t plus delta? Equal to y. So I can write a equal to, acceleration equal to, negative omega squared y. Is that right? Yes. Acceleration equal to negative omega squared y. There, of course, you know what omega is. Y max. What is the maximum value of the amplitude? Maximum value of the amplitude is a. What is V max? We just talked about it in the previous slide. The maximum value of the velocity is a omega. You can actually get right from here, from the velocity of the equation. You see? Any cosine or sine function has a maximum value of 1. Do you know that? Cosine or sine will oscillate between -1 and +1. The maximum value of cos omega t plus delta is 1. Therefore, V maximum will be a omega. That's right. In that case, can you tell me what is the maximum value of acceleration? What is the maximum value of the acceleration? Well, when this is maximum, the value of sine omega t plus delta will be 1, because that is the maximum value of a sine function. Therefore, a max equal to a omega squared. Don't take the negative sign when you talk about the maximum value. Now, you must remember this. The maximum displacement is amplitude a. Maximum velocity is a omega. maximum acceleration is a omega squared. We need them to solve problems. And omega equal to square root k over m. I asked you that about a minute ago. And also omega equal to 2 pi divided by t. Is that right? Yes. And that's the same as 2 pi times f. And relation between frequency and the period, f equal to 1 over the period. You got to keep track of all these formulae. How about the potential energy of a stretched spring? Now, if the stretch is horizontal, we call the displacement x. So U potential energy is 1/2 kx squared. And if it is a vertical displacement, we call it 1/2 ky squared. And the kinetic energy of the oscillation is k equal to 1/2 mv squared. The total energy of simple harmonic oscillation is 1/2 ka squared. And also F equal to negative kx. When a string is stretched, the restoring force is proportional to the displacement. F equal to negative kx. We did that in physics 1. And this is actually called Hooke's law. Is that right? All right. The maximum kinetic energy occurs at the equilibrium position. Maximum kinetic energy is 1/2 mv max squared. And that is the same as the total energy, which is 1/2 ka squared, or Vmax equal to omega a, this is a repeat, and omega is square root k over m, and you can write them in many, many forms. All right, let's do a problem. Now read this problem carefully. A 2 kilogram object is attached to a horizontal spring. So this time you have a spring that oscillates horizontally with a force constant k equal to 5 kilonewton per meter. Watch that unit. The spring is stretched 10 centimeters from the equilibrium position and released. Now remember, when you read a problem, you need to understand this. Now the spring is stretched 10 centimeters. This is the unstretched spring. It is stretched 10 centimeters means that is the maximum displacement it is going to have. In other words, that is the amplitude. You see that? The amplitude will be 10 centimeters. All right. What is the period, the frequency, the amplitude? What is its maximum speed? You have plenty of information there. Let's start with picking the data. Now, this is how the spring oscillates. This is the equilibrium position. It is stretched 10 centimeters to the right. So the mass of the object is 2 kilograms. The value of K is 5 kilonewton per meter. It is 5,000 newton per meter. Amplitude is 0.1 meter. You see, it is stretched from the equilibrium to the right extreme of 10 centimeter. Is that right? That is the amplitude. Now, what is the period? The period of an oscillating spring is given by, period is 2 pi square root m over k. Do you remember that? I think I forgot to include this equation when I picked equations. But look at the equation there. The period of an oscillating spring is 2 pi square root m over k, and we have all those values there. So put m equal to 2 kilogram, k is 5,000 newton per meter, and put that in your calculator. I got it as 0.126. Let me give you a word of warning. I always, most of the time, make mistakes in my calculations. And I haven't gone back and checked it. You know why? I want you to check it. So don't just sit back and watch the lectures. Be an active participant when you learn. So take your calculator and do this with me as I'm doing it. So the period is 0.126 seconds. All right. If you have the period, do you know how to find the frequency? What is the relation between period and frequency? Well, they are related in such a way that one is the reciprocal of the other. So we got the period as 0.126, and therefore the frequency is 1 over the period. That will be 1 over 0.126. That is 7.94 Hertz. It means the object will go back and forth 7.94 times a second. What is C? What is the amplitude of the motion? Well, that is given to you. What is the amplitude of this oscillation? Amplitude is 0.1 meter. You don't need to calculate it. Well, the amplitude is 10 centimeter, which is 0.1 meter. All right, what's the next one? What is its maximum speed? What is the equation for maximum speed? Anybody quickly? Well, first of all, you need to find the angular frequency omega, because you know, if you look back on your equation, maximum speed is A omega, amplitude times omega. So you need to find omega. All right. Do you know an equation which we can use to find omega? Can you get that equation for me? Omega equal to 2 pi f. We know the frequency. We just calculated the frequency. I don't have that value here, but I thought it was 7 point. Anybody remembers that? Well, 7.94. So omega is 2 pi f. Use the value of f. You get as 49.9 Hertz is omega. Now, once you know omega, how do you calculate your maximum speed? The maximum speed Vmax is given by what? Vmax equal to A omega. We know the amplitude, we just calculated omega, so that will be amplitude times omega. That is approximately 5 meters per second is the maximum speed. What is its maximum acceleration? What is the equation for the maximum acceleration? Anybody? Maximum acceleration is A omega squared. Well, we've got all those quantities there. The acceleration of a simple harmonic motion, well, I really don't need to use this. I know the maximum acceleration is, you see, the maximum value of y is A. Therefore, maximum value of the acceleration is omega squared A. Remember, negative sign will give you the minimum. If you take away the negative sign, it will give you the maximum. So the maximum acceleration is omega squared A. Omega we know, A we know. So the maximum acceleration is 249 meters per second squared. All right? I would like you to go back and do this one more time. All right, let's go back and see what is left. When does the object first reach the equilibrium position? Well, remember, the object is released from the extreme right. That means when you hit the clock, when you start your clock at t equals 0, the object is at the right extreme. And when will it come to the equilibrium position? It will reach the equilibrium position in a quarter of a period. Is that right? Because the period is the time taken to come to the equilibrium, go to the left extreme, come back to the equilibrium, and come to the starting position. That's when you have one complete oscillation. The time taken for one complete oscillation is the period. And therefore, the time taken to move from the right extreme to the equilibrium position will be a quarter of a period. Is that right? I think so. Since the object is released from the extreme right, it reaches the equilibrium position in 1/4 of a period. And you know we calculated the period t equal to 0.126 seconds. And therefore, the time taken to reach the equilibrium position will be a quarter of that. And what is that equal to? 0.032 seconds. And what is the acceleration at this time? At what time? What is the acceleration when the object comes to the equilibrium position? Anybody? At the equilibrium position, there is no acceleration. Acceleration is maximum at the two extreme positions. Acceleration is 0 at the equilibrium position. Well, in fact, in this problem, we touched on every concept we discussed in the lesson on oscillations. So I would like you to go back and do this one more time, okay? Let's do another problem. A 5 kilogram object oscillates on a horizontal spring with an amplitude of 4 centimeters. Again, you have a horizontal spring oscillating. Its maximum acceleration is 24 meters per second squared. The moment you hear that, you must say, hey, I know an equation for maximum acceleration. Anybody know what the equation is? Maximum acceleration is a omega squared. And you can see amplitude is given there. Maximum acceleration is given there. I can therefore find omega, the angular frequency. Is that right? That's the way to think about the problem. Find A, the force constant, B, the frequency, and C, the period. You've got to find the force constant K. Okay. Can you suggest to me a method? How do we find K? Well, I just gave you a method by which you can find your omega. And omega, you see, if you know the equation for omega, you know it contains K. All right? Okay, so let's write down what is given there. You know mass is 5 kilograms. Amplitude is 4 centimeter, 0.04 meter. Always use the proper units. All right, so the spring is pulled 4 centimeter and released. The amplitude of oscillation is 4 centimeter. The maximum acceleration is 24 meters per second squared. And we need to find the force constant. So obviously, if you want to find the force constant, first we need to obtain omega, the angular frequency. Then you got A max equal to omega squared A. You know the value of A max, which is 24 meters per second squared. You know the value of amplitude, 0.04 meter. Therefore, you can calculate omega squared. And omega squared, you know, or you should know, is K over M. Omega is square root of K over M. Therefore, omega squared is K over M. Now, you see, if you look at this, you know the value of A max, you know the value of M, you know the value of A. Can you now calculate K? All right, solve for K there, can you? K equal to A max multiplied by M divided by A. That's right. A max multiplied by M divided by A. I hope you understand when I show you this. A max equal to K over M A, cross multiply. A max times M and divide by A, you get K. And you know all these values. A max is 24 meters per second squared. M is 5 kilogram. And A, the amplitude is 0.04 meter. And that is 3,000 Newton per meter is the value of K for that spring. Well, part B is find the frequency. How do you find the frequency? Well, if you know omega, don't you know the value of omega? Yes, we know omega squared is K over M. So let's go and do it. Omega squared equal to K over M. And we just calculated K, we know M. That means omega squared is 600. Look at the unit of omega squared. Omega, the unit is hertz per second. Omega squared per second squared. Therefore, what is omega? Omega is square root of that, which is 24.5 per second. Per second is also called hertz. Alright? Once you know omega, you know that omega equal to 2 pi f. So to find your frequency, what do? Divide omega by 2 pi. F equal to omega divided by 2 pi. And omega is 24.5 hertz divided by 2 pi. And that gives you the frequency of oscillation as 3.9 hertz. Okay, if the frequency of oscillation is 3.9 hertz, what is the period? What is the relation between frequency and period? Well, the period is the reciprocal of the frequency. Period equal to 1 over f, and f we just calculated. Therefore, the period is 0.256 of a second. Very good type of problem, and you must try that one more time on your own. Okay? Let's go and try another problem. A particle in simple harmonic motion has a displacement x equal to, I want you to read this completely, this is cut off from here, x equal to 0.4 sine 3t plus pi by 4. Let me write that down over here. X equal to 0.4 sine 3t plus pi by 4. Now, let me write down below it the standard equation. The displacement equation is x equal to a sine omega t plus delta. Now, what it tells you is the amplitude of oscillation is 0.4. You see that? Compare the given equation with the standard equation. That means your value of omega equal to 3 and the value of delta is pi by 4. The phase angle is pi by 4. So those are the information that are contained in that equation. So the moment you see the equation, you have got many information from there. Alright? Let's use those to find these. Where is the particle at t equal to 0? So to find the position of the particle at t equal to 0, what all you need to do is put that t equal to 0 and solve it on your calculator. What will be 0.4 sine pi by 4? When t equal to 0, that will be 0. This will be now sine of pi by 4. Anybody tell me the value of sine pi by 4? Well, you don't need to know it. Your calculator knows it. It's nice to know that. All right, let's write down these steps. So, what do we have? The displacement of a simple harmonic motion is x of t equal to a sine omega t plus delta. That gives me a equal to 0.04, omega equal to 3 hertz, 3 per second, and delta, the phase angle, is pi by 4. We need to find the position of the object at t equal to 0. All we need to do is put that t equal to 0. So that will give me, when t equal to 0, this will be a sine, that is 0.4 sine, 3t becomes 0, so that will be sine of pi by 4. And put that in your calculator. 0.4 sine pi by 4 is 0.28 of a meter. So, at t equal to 0, the position of the object is 0.28 meter. What's B? Where is the object at t equal to 0.5 second? Alright? In order to find the position at t equal to 0.5 seconds, what do? Come over here and put the value of t equal to 0.5. Let's do that. It will be x of 0.5. The position x when time t equal to 0.5 is 0.4 sine omega t, 3t. You see, I put t equal to 0.5. 3 times 0.5 is 1.5 plus pi by 4. All right, let's calculate that. It gives me 0.302 meter. Okay, what's the next one? Find the frequency f and the period t. Now, anybody help me to find the frequency f? Well, we know omega. If you know omega, you know your frequency. All right, how is the frequency related to omega? The angular frequency omega is given by omega equal to 2 pi f. Therefore, if you know your angular frequency, you know your frequency. So f equal to omega divided by 2 pi, that is 3 hertz divided by 2 pi, that is 0.48 hertz is your frequency. Well, I wrote down that early there. I don't know why, but it just happened. So, now, but the important thing is, if you know the value of your omega, then you know the value of your frequency. See that? Okay. If you know your frequency, then you know the period. How? Period is 1 over the frequency. T equal to 1 over the frequency. That is 1 over 0.48. That will be 2.1 second. Another important type of problem. Okay, let's do another one. An object of mass m is supported by a vertical spring of force constant 1800 Newton per meter. When pulled down 2.5 centimeter from equilibrium and released from rest, the object oscillates at 5.5 hertz. All right, tell me, what are the given data here? Anybody tell me, what are the relevant data we can pull from there? Well, first of all, we know the value of K. K is 1800 Newton per meter. Then we are told that the spring is pulled down 2.5 centimeter from the equilibrium and released. What does that mean? It means, now, look at this. Oops. Give me a second. Now, this is the equilibrium. You pull it down 2.5 from the equilibrium and release it. That means that will be the maximum displacement. You see that? The maximum displacement is 2.5. This is the equilibrium position. You pull it down 2.5 centimeters and release it. Now it's going to come back to the equilibrium, go up, back to the equilibrium. That means the amplitude of oscillation will be 2.5 centimeter. That is an information that you need to pick. And then it says the frequency of oscillation is 5.5 hertz. Let's write down those. Always when you want to do a problem, pick your data. It's very important. All right, here you have the spring. The amplitude is 0.025. The spring constant is 1800 Newton per meter. Amplitude is 0.025 meter. And the frequency of oscillation is 5.5 hertz. That's the data we know. What do we need to do? Find m, find the mass of the oscillating object. Can you form a strategy for doing this problem? Well, look at the way I'm going to argue this out. I need to find m. Now, you need to look around. Is there any equation that gets connected to something that we know? Well, you know that m is connected to omega. Is that right? What is the relation between omega and mass m? Omega equal to square root of k over m. You see, I know my k. And I can therefore obtain a relation for omega. Is that right? That's right. If I can find omega, I can find m. Well, that's the way you must think about it. So to find m, we first find omega, the angular frequency, and use the relation that connects m to k. That's the way you must think about this problem. Now, first of all, because you know the frequency is connected to the angular frequency, omega equal to 2 pi f. And because you know the value of f, you got now omega. Omega equal to 2 pi times 5.5, that is 34.6 hertz is the value of omega. And now, connect omega to m and k. You now know omega, you know the value of k, therefore you can find m. You know omega squared equal to k over m. Is that right? Omega equal to square root of k over m, but it's easier to square it. Omega squared equal to k over m, and therefore what is k equal to? We need m. Can you solve for m from there? Well, m will be equal to k over omega squared. So m equal to k over omega squared, that will be 1800 divided by 34.6 squared, that is 1.5 kilogram. So we found m. Find the distance the spring is stretched from its natural length when the object is in equilibrium. I don't know whether you understand that. Well, you see, this is the natural length of the spring. Now, when you put that mass in there, it's going to stretch, the spring is going to be stretched so that the object comes to the equilibrium position. You need to find out how much is the stretch. Is that right? That's what you need to find. That's the natural length. When you suspend the mass, it is stretched there. What is that stretch? I don't know whether you actually saw that because I was covering it. Let me show that one more time. That's the natural length of the spring. When you suspend the mass falls to the equilibrium position, stretching the spring. You need to find the stretch of that spring. That's what you need. All right. The force stretching the spring is F equal to mg. Is that right? Yes? When you suspend that mass, the force stretching that spring will be F equal to the weight of this. And the mass is 1.5 kilogram, and therefore the stretching force is 14.7 Newton. Well, if y is the distance the spring is stretched from the equilibrium position, F equal to ky. Is that right? The stretching force is proportional to the displacement. But I haven't used the negative sign yet because we only are interested in the value here. So F equal to ky, you now know F equal to 14.7 Newton. You know the value of k, therefore you can find your y. What is y equal to? Y equal to F over k, and F is 14.7, k is 1800 Newton per meter. Therefore, that will be 0.0082 meter. That's a very small stretch, is that right? Why? Because the spring constant is very high. What does that mean, the spring constant is very high? The spring is a very hard spring to stretch. This is a low k. The value of k for this spring is about 26 Newton per meter. And the spring we are using is 1800 Newton per meter. So it will be very hard to stretch it. All right, another problem. A 3 kilogram object oscillates on a spring with an amplitude of 8 centimeter. Its maximum acceleration is 3 meters per second squared. Find the total energy. Well, if you want to find the total energy, well, what's the equation for the total energy? Total energy is 1/2 kA squared. Is that right? All right. You have a spring oscillating a 3 kilogram object and the amplitude is 8 centimeter. Well, the total energy is 1/2 kA squared. We know A, that means we need to find K, the spring constant. All right. Amplitude is 0.08 meter. Mass of the object is 3 kilogram. A max, the maximum acceleration is 3.5 meters per second squared. All right. Can you tell me, is there enough information for you to find the value K of that spring? Anybody tell me what is the equation for A max? Well, A max is, yes, omega squared A. That's right. The total energy E is 1/2 kA squared. We have A, the amplitude. That means we need to find K. How? Well, first we find omega, the angular frequency, because you know that K is related to omega, as omega is square root of K over M, or omega squared is K over M. So let's find omega. Is there enough information to find omega? Well, A max you know is A omega squared. And therefore, omega squared equal to A max divided by the amplitude A. You know both these values. A max is given, amplitude is given, therefore omega squared equal to 43.75 per second squared. And how is omega squared related to K? Recall that again. Omega squared equal to K over M. Let's do that here. Omega squared equal to K over M. And I want to find my K. My K is M omega squared. Is that right? So K equal to M omega squared. M times omega squared is 43.75. That's my K. Now, we have M equal to 3 kilograms, so I can use that. Omega squared is 43.75. M is 3. And so K is so many Newton per meter. That will be 131.25 Newton per meter. All right? A good way to find out K, I want you to look through the various steps of that problem. We now have our K, we have the amplitude. What is the total energy? Total energy is 1/2 kA squared. And use all the given values. That will give you the total energy as 0.42 joules. A good problem. All right, let's try another one. A spring of force constant K equal to 250 Newton per meter is suspended from a rigid support. Form a mental picture when you read the problem. An object of mass 1 kilogram is attached to the unstretched spring and the object is released from rest. How far below the starting point is the equilibrium position for the object? Again, you need to understand this problem. You see, this is the unstretched spring. Don't think that when you suspend the mass and leave it, the mass is going to stop at the equilibrium. Is it going to stop at the equilibrium? No, if I drop it, it's going to go all the way to the lower extreme. That means it has crossed the equilibrium. So, you have an object of mass 1 kilogram is attached to the unstretched spring and the object is released from rest, like that. How far below the starting point is the equilibrium position for the object? Well, is it reasonable to assume that if the object is going to go all the way to the lower extreme, that means the distance it has fallen is at the upper extreme, it's going to go all the way to the lower extreme, the equilibrium will be somewhere in between. Is that right? Okay, let's talk about that as we move on. Well, that's the question we have, the starting position, and that's the lower extreme is going to fall. Okay. K value of the spring is 250 Newton per meter. Mass is 1 kilogram. When the attached mass is released, the force stretching the spring is. What is the force stretching the spring? F equal to mg is the weight of the object. Now, and that is equal to 9.8 Newton. Why? Because m is 1 kilogram. G is 9.8. Now, this force stretches the spring by a distance y, is that right? Such that F equal to negative ky. We don't need the negative sign. Now, y is the distance of the equilibrium position below the starting position. That's right. You see, this y is now the distance from the starting position to the equilibrium. And what is that y equal to? Y equal to F divided by K. Forget about the negative sign. F is 9.8 Newton. K is 250 Newton per meter. And that is 0.039 meter. That means when the mass is allowed to fall, if you allow this to fall gently, well, it is going to be stretched so that the object comes to the equilibrium position. But if you drop it, the object is going to go past the equilibrium all the way to the lower extreme. Now, here F equal to ky, y is the distance it falls to the equilibrium. That's your y. That means if it falls the distance y from the rest position, it will go an equal distance to the lower extreme. Is that right? I think so. Okay. Now, the equilibrium position is 0.039 meter below the rest position. That's the equilibrium position. The object now will oscillate with an amplitude, so that gives us the amplitude of oscillation. The amplitude of oscillation is now 0.039 meter. Well, in that case, where will be the lower extreme? From the equilibrium position, the mass will move down to the lower extreme, a distance equal to the amplitude. That means it will go down another 0.039 meter from the equilibrium position. Is that right? So the total distance it will move will be 0.039 plus 0.039. Okay. Let's look at more of this. We found the distance it will travel will be 0.039 plus 0.039. That will be 0.078. Is that right? Okay. What is the B part? We did that one, I think. C part. What is the period of oscillation? What is the period of oscillation? The period of oscillation, T for a spring. Anybody can recall that? T for an oscillating spring is 2 pi square root m over k. And do we have all those values? Yes. We know m is 1, k is 250, therefore t is 0.4 seconds. What is the speed of the object when it reaches the equilibrium position? Now remember, the speed of the object at the equilibrium will be the maximum speed, Vmax. Anybody tell me what is the equation for Vmax? Well, you've got to recall all that. Well, let's first of all talk about the total energy. That is D, is that right? Now, the total energy is 1/2 Ka squared. And at the equilibrium position, all that energy is kinetic energy. So we say 1/2 Ka squared equal to 1/2 mv max squared. Can you calculate V max from there? Can you solve for it? V max equal to square root of Ka squared over m. Do we know all these values? Yes, we know all those values. We know our K, we know our A, the amplitude, and we know our M equal to 1 kilogram. So that will be 0.62 meter per second. And that is the velocity when the object reaches the equilibrium position. Okay, this is again a very important type of question. Please take some time and review it. Well, I think we spent quite an amount of time solving problems using the concepts we developed in this lesson. Okay? I want you to go back and do all of them. Now, do all the homework. I have worked out the homeworks for you, but don't look at the homework solutions until you do them on your own. Okay? And if you have any problems, get back to me. Well, I will see you for lesson 2 later on. The description